Okay, right. So that's sort of just a little detour into measurement. As we know, it is a hell space. I have to eat sticky sweet things. Here's a thing. Okay, so I know this. I presented this work at SFI in 2000. You know, it's all good. I mean, I'd met Wes before, and we'd talked a lot, and we'd had a lot of. I'd actually been there to try and work with him. So, but I'm presenting like this is not working, guys. It's got 3,500 citations. It's a yeah. Our work has got about 500 citations, which is totally fine. It means it exists, and it's people are familiar with it. But it is hard for things to catch up. Okay, and his quote when we showed this, "I don't like statistics." Oh my God, unbelievable. So, but he's changed a lot. Now he thinks data is their biggest contribution, which is the stuff they did for city scaling, which is really Louis Bettencourt. So. What you could do is say, okay, evolution is producing bigger things, so let's kind of look at how the scaling works as we made bigger and bigger things. Of course, things get smaller on islands and there's that sort of stuff, but evolution has sort of opened up this envelope of size. So there are a lot of little critters out of our 391 that are less than 100 grams. And if you do the regression there, and you'll get these exponents, right? So this is within error, certainly 2/3. It's not encompassing 3/4. I guess I won't get through all of it, but I'm sort of going to sort of show you sort of a somewhat careful attempt to do these regressions rather than just sort of put a big line through the whole thing, but just sort of see, does it hold up in smaller parts and so on. So we're going to open this window up as we go to, right? So we're including bigger and bigger organisms, and you can see how the numbers go up. And so this exponent, very close to 2/3, very close to 2/3, certainly with the error. Still good for 2/3. Now it starts to fall apart a little bit. So it's these larger ones that are kind of tugging the thing up. And they may well be different, right? Because we're starting to get to elephants and things, and they have to cope with gravity and in ways that your little furry creatures don't. But there are a lot of things running around on the Earth that are, back in this category. And certainly for birds, so if we do the same thing for birds, which is here, then it doesn't really ever deviate from 2/3, right? So big error down here when we've got 160, and then it's going up. I mean, this is 2/3-ish. It's crazy, so weird. So 100 kilograms is going to be an ostrich. Yeah. And what do we get up to? Yeah. So elephant. There's one elephant in this data set, but it's they're big units. Birds definitely have a lower density, yeah. So the presumption is for these groups that the density is similar across them. So when we say mass, we also mean volume. I'm sure someone has measured that. I mean, there are there's maybe I mentioned it, but there's a paper that I came across somewhere where for a number of organisms, they had figured out the total amount of mitochondria in the organism by sort of, removing life from it, but also burning it in some way. Like there was some sort of thing that got titrated out the mitochondria. Something happened. It was like the charred remains, and then there was a little sort of pile of mitochondria. It felt like that. There's also blood volume. This will come up. Incredibly, there are papers that appeared in Nature and so on that had blood volume scaling as mass to the 4/3. Just thinking about that for a second, right? So if blood volume is scaling as mass to the 4/3, it's not going to work out, right? I mean, it's okay for the mouse, but once we get up through a few orders of magnitude, it's not going to fit inside, right? So, oh man, this is a really strange. Scaling is a tricky business, I suppose, but people, because you can do the back of the envelope stuff and just it's like, it all works. But we'll see an invoking of a fourth dimension. It's really strange, really strange. But I think that's right, and I think that's sort of an important aspect of why these things need to be separated. And fish are just that's a hard business. Like if you want to get up to whales and stuff, that's hard. Yeah. Sometimes there's data, I think there's been data for whales, but I think it's been made up, basically. That's terrible. Like you'll see a point on a graph and it turns out it's all made up. Okay, so fluctuations. So what we could do is we've got our speckling, right, of points. And so what we can do is remove the best line of best fit and then look at the distribution of the residuals. Right, so we look at the distribution in log space. And if you look at the distribution of residuals, this is for the first, it's not for all of them. It's up to maybe 10 kilograms, I think, in this case. So we're going to divide this is based on metabolism, mass to the 2/3, and then make a histogram out of it. And so we've got this is a frequency, and then the thing that we could do is usually there are a number of nice tests that are non-parametric to compare distributions, and Kolmogorov-Smirnov test, which is not how much vodka you can drink, but it's which is another Russian test. But this is a really a beautiful thing, and so some often called just the KS test. So if you're trying to compare two distributions or a perfect, one you have a theoretical one to a real one, this is one way to do it. And it's not bad. I mean, there's a little bit of a spike in the middle, but certainly from a statistical blah, 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 it's not bad. So you kind of expect that. It's not too bad. That there's a fit, it's going to have some fluctuations. I really want to see a plot with a koala's brain on it. We talked about the koala, right? Yeah, so disappointing. They have tiny brains. And they're smooth. So bad. They really, really are dopey. Okay, so let me just show you this, I suppose. Maybe we can mention it again. So we can do some things like this. Let's say we believe it is 2/3, or we believe it is 3/4, or we believe it is some exponent, any range from 0.6 to 1. We could do that. So a couple of things like that. So this is, using some of these old data sets. This is the full mass range. So this is probably, if we had a 2/3 law, what's the probability that we could get this Kleiber stuff coming out, right, with some fluctuations? So we wouldn't expect it, right? This is a low probability sample, and it's just 13 things, so that's pretty bad. 3/4, yes, this is pretty good, right? Not bad. And again, so it doesn't fit here for this Brody data. This is the livestock stuff. Does not fit for Heusner, which is the big meta-analysis of the early 1990s. And 2/3 is totally great for birds. I mean, this is super duper. Not so good. 10 to the -15 is not really. It's always, remarkable. With such large data sets now, you sometimes see 10 to the -100 or something. It's like, it's madness. But if you break it into, and this is for mammals, if you break it into 10 kilogram up below and above 10 kilograms, then you get sort of a different thing appearing. That's the measuring exponents of these. Now we only have five organisms in the Kleiber data set. 2/3 looks tremendous now. 3/4 is not rejected, so 5 looks very good. Brody's kind of a mess. The Heusner data really looks like 2/3, right? But not quarters. So this is better thing. So what I'm trying to here is Kleiber have just 13 things, tiny samples, and find regression to the seams. And work just appeared on this the other day, basically saying it's a mixture of power laws and all sorts of things. Again, not the first people to do it. For greater than 10 kilograms, maybe the exponent, I'm not saying it's 3/4, but it does maybe curve up. That could be an artifact of measuring those larger organisms back in the day. So that sort of holds together. So the probably it's a 3/4, not bad. Heusner doesn't work. It's actually that exponent's too large. So there may be a break in scaling. Breaks in scaling happen all the time. It happens in distribution, the probability of earthquakes of given sizes, and there's a reason. This could be to do with again, gravity and the way bones start to be structured. So here's the thing. any exponent you want, we're going to fit the prefactor and then look at the residuals. And if the residuals are, right, so if we've got the wrong exponent, the residuals will be correlated with each other, right? They'll tend to be below and then above the line, or above and then below the line. If it's a really good fit, then they should be just sort of like randomly jumping around from side to side. There are various ways. The Spearman rank correlation, beautiful thing, non-parametric, where you just simply order things, right? So we'll take the x's and the y's and we'll rank them by size, and now you just have 1 to n and 1 to n shuffled. It's a permutation problem. Primo stuff, really nice. Non-parametric, you don't have to know what the distributions are. So it's the spiffing Spearman rank order correlation coefficient, and you can look that up. It's a beautiful thing. Students, numerical recipes in C. I know this is sort of an old thing. Great explanations. So if you do that, so the game now will vary from 0.6 to 0.8. We'll allow all those exponents, and we're looking at how do the residuals look in terms of are they sort of just bouncing around that line of fit, or are they sort of from one side to the other? And so this is for mammals up to just 3 kilograms. It's on a log scale, 10, 32 here, and then all of them in this Huizner data set. And so you see this is the p-value. So you see that it's like really pretty great for 2/3, and absolute, this is 10 to the minus 4.5, no good here, right? So this fit doesn't work. Pretty great again here, pretty great again here, and it's starting to move across, but really 3/4 is not in the game. Wow, there is so much arguing that comes after this paper, and particularly in the 2000s. And I mean, we kind of lit a match, I suppose. But this is striking to me, and if you do it for birds, similar kind of thing, right? So there are lots of ways to think about this, but this is a p-value, right? There's a probability that your hypothesis of a 0.6 to 0.8 exponent could produce this sort of this speckling of points, such with presumption that if we've got the right best fit line, then they'll be uncorrelated, right? The residuals will be uncorrelated. I should say the dashed lines are 0.05 and 0.01. I'm sorry, I'm going a little long, but I just want to finish this piece. So class et, and then I've linked this in. I had to add that. These are usually for measuring power law decays, but that's another approach. So anyway, so the upshot is maybe 2/3 works for birds. Mammals, maybe only up to 10 to 30 kilograms. Maybe it's a different scaling regime. There's work from economists. There's a break in scaling in the way limb lengths work, but we'll see. Anyway, if we really do actually have non-isometric growth for shapes of organisms, then we're going to have lower metabolic scaling. That's something we'll get to later on. So pancake cows are not going to work out. Science. Okay. Sorry for going a little long, but it's madness. It's madness.